We are Group 12 and our project is Cloud-Based Energy Conserving Smart Ceiling Fan System, which is supervised by Dr. Tushar Ratnayake. Motivation for the project. In a country like Sri Lanka, fans are widely used when compared to air-conditioned systems. But most of the time, their operation is unattended. Energy saving can be achieved by adjusting fan speeds according to adequate thermal comfort levels, but people are reluctant to adjust fan speeds using manual controlling methods regularly. The Internet of Things is a trending topic which relates to improving the quality of life. Also, people tend to make informed decisions when they are aware of their energy consumption. Problem statement. Majority of the fans do not contain automatic control systems. Even if they do, they are very expensive and the entire fan system has to be replaced as a whole. Individual operation of multiple fans is difficult. For example, we do not change fan speed or switch off during night, although the fan operation might not be required. Objectives. Design and implementation of efficient ceiling fan control system for already existing ceiling fans to achieve thermal comfort. Achieving energy saving by systematic control of the fan by speed change or switching off of the fan. Real-time data visualization and data monitoring through mobile and web interfaces.
This is the overall illustration of the proposed system. Functionality of the system is shown in this block diagram. Fan controller is designed in a way that it can replace existing fan regulators. It consists of a Node MCU microcontroller for bidirectional communication of data and control signals, a relay module to switch speed levels of the fan, and a current sensor for real-time current monitoring. Sensor node consists of a DHT11 sensor to measure temperature and humidity, and a microcontroller to communicate collected data with the control hub. Control hub consists of a Raspberry Pi 3, to which all the devices are connected via MQTT protocol. It is connected to the AWS cloud through the Wi-Fi interface. A local dashboard is also installed in the control hub for local operation in case of internet disconnectivity. Web and mobile applications are hosted in the cloud service for remote monitoring, controlling and analysis purposes. This shows the physical implementation of the controller. This is the physical implementation of the sensor node. Here is the physical implementation of the control hub. This shows the mobile interface of the dashboard.
Here you can see the web interface of the dashboard. This section shows current operating mode and speed level, operating mode switch which allows the user to switch between auto and manual modes, and a set of buttons which allows switching between speed levels in manual control mode. This section shows the real-time values of measured temperature, humidity and power consumption of the fan. This graph indicates the temperature variation of the considered area with the time. Variation of fan power consumption with time can be seen in this graph. In this section, we can see the total energy consumption of the fan during a period of 24 hours and energy saving which is calculated compared to a practical operating model for the daily usage of a ceiling fan. All the temperature, humidity and power consumption data are being uploaded to the AWS server continuously in the background for analysis purposes. This illustrates the operation of the web interface fan controller and the fan. This illustrates the operation of the mobile interface, fan controller and the fan. A time-lapsed recording of the dashboard operation is shown here. When the highlighted area is considered, we can clearly see the different power consumption levels at different fan speeds. When both highlighted areas of temperature and power are considered, we can see that the temperature gradually reduces and stabilizes at a minimum temperature level with increasing fan speed. During this instance, we can see that when the fan is turned off, temperature will rapidly increase. Now, at this instance, we can see that the minimum possible temperature is achieved by operating the fan at speed level 3 rather than at maximum speed. If the system can identify such scenarios and change the fan speed accordingly, a significant amount of energy can be saved. This is the theory behind the main control concept used in this system. Controlling programs identify such scenarios and save energy while maintaining the temperature within the thermal comfort zones. Thank you.